Hi everyone, so this is going to be topic D.8, which is about nuclear medicine. And we'll see how radioisotopes can be used to diagnose and treat certain medical conditions. Now, what are radioisotopes? Radioisotopes are also called radioactive isotopes. These isotopes, they are unstable, and the instability is because of the nucleus. So depending on the number of neutrons that it contains, if it has too few neutrons or if it has too many neutrons, then it becomes unstable. And when it becomes unstable, it's going to break down into a stable nucleus, and usually it gives out small particles. These particles can be alpha particles or beta particles, and at the same time it gives out energy, right? So why are some of these isotopes unstable? It's because of the number of neutrons. Now, the energy that is liberated from these radioactive isotopes is useful to enhance medical imaging, or it is also used to kill cells in targeted area. And sometimes the nuclei are made to be unstable by bombarding the nucleus with neutrons or helium nuclei at high speed, and this is called induced nuclides. Now, here, this is called the parent nucleus. So what you start with is called the parent nucleus, and what you end up with, these are called the daughter particles. So parent nucleus will give you the daughter particles. Now, the daughter particles can be alpha particles, beta particles, or gamma radiations. Now, we say alpha radiations, but these are mostly particles, and so alpha particles are actually helium atoms. They are helium nucleus, so it's represented by alpha 42, this symbol, or helium 42, like this. So these are helium nucleus. The beta particles are basically electrons, so it's represented like this, 0, -1, or also electron 0, -1. Right, so it's basically an electron. And gamma radiations, this is not a particle, this is actually a radiation. It has no mass, it has no charge, so it's represented like this, gamma 0, 0. Right? Now let's see in details alpha particles. So alpha particles, they are nucleus of helium 4. So 2 protons, 2 neutrons. So the charge is actually +2, and the relative mass, so if I'm going to write relative mass, this is 4, and we represent the helium nucleus like this, He42, or we can also say alpha 42. Now, when we have decay, radioactive decay, parent nucleus is going to give daughter nuclei, but the sum of the masses should be the same on both sides. So for example, if I have bismuth 212 decaying into thallium, and this is emitting an alpha particle, so alpha 42. So when you add the atomic masses on the right, it should give you the atomic mass on the left. So together it should give you 212. So to find the atomic mass of thallium, so we're going to do 212 minus 4. So this is going to be 208. And similarly, here the atomic number should add up to give what is on the left. So then 83 minus 2, that's going to be 81. So this is the atomic number for thallium. So what is on the left should equal to all the particles, all the masses on the right. Now if you look at beta radiations, so beta radiations we represent it like this. 0 minus 1. So this is basically an electron. And when a beta particle is produced, a neutron from the parent nucleus is converted into a proton. So if I take, for example, bismuth again, 21283, producing polonium and a beta particle. So this is 0 minus 1. So then here this is going to be 84, because 84 minus 1 gives you 83. So it matches this number. And this is going to be 212 similarly, similar to this, because this is 0 here, right? So which shows that it's going to be one neutron which is converted to a proton. So you have one additional proton here. Now, if we look at gamma radiations are only energy, right? So they do not result in any changes in the nucleus, in the atomic number or the mass number. So if we have, let's say, the same example, bismuth 212, if this is emitting gamma radiations, so it's going to produce bismuth itself to 1283 plus gamma radiations, which is 00. Now, sometimes you will see that this is shown as 212M giving 212. Or if we take, for example, technetium, this is another example, technetium 99M giving technetium, without the M now, plus gamma radiations. Now, what does the M mean here? The M means that M means metastable. Metastable means that it exists as an excited state. But when it emits the gamma radiation, now it's back to the ground state. This is what the M means. So it's the same thing, except that this is in the excited state. And when it produces back technetium in the ground state, it releases energy. And the energy that is liberated is used for imaging. So what happens is that the medical team is going to administer this isotope in the excited state to the patient. And this is going to bind to particular areas of the body. And then when it binds to particular areas of the body, so then it's going to decay and to give out energy. And this energy is detected by the scanners. And when they detect the gamma rays given out, it gives an imaging of what is happening inside the body of the patient. So this is how technetium is used in the medical industry. Let's now see these questions. So you have the alpha decay of radon 219. So we're going to start by writing the formula, the symbol, of radon. So 219, and I'm going to be using section 5 of the data booklet. So I find radon here. So this is 86. And this is going to undergo alpha decay. So I'm going to get an alpha particle for 2. So this should be an element with atomic number 84 and atomic mass 215. So I'm going to look for the element with atomic number 84 in section 5. You could also use the periodic table. So 84 is polonium. So this would be PO. Beta decay of carbon 14. So carbon 14, we know atomic number of carbon is 6. And this undergoes beta decay, so 0 minus 1. So this would be an element with 7, 14, and 7, 14. This is nitrogen here. So this is nitrogen. So we have the equations of those. Let's try this one. So it says that bismuth emits either alpha or beta particle, and the daughter nuclei in both cases undergo further decays to produce the same isotope lead-208. So let's write this down. So bismuth 212 This will emit an alpha particle for 2 and will also emit, or could also emit, a beta particle. And after this, the daughter nuclei undergoes further decay, and in both cases it produces lead-208. So we have to write the equations for this. So let's find the atomic numbers for bismuth and lead. So I'm going to use section 5. This is in alphabetical order. So 83, and lead is here. So lead is 82. Once we have this, I'm going to write the daughter nuclei from the first decay. So this will be a particle with 81 and 208. And with beta decay, this will be 84 to 12. And I'm going to find these elements in the data booklet. So 81 is thallium and 84 is polonium. So this will be thallium and this will be polonium. So I have my two equations and I can rewrite them down. So as such, we have the two equations that are possible for bismuth, one producing alpha particle and one producing beta particle, and both of these daughter nuclei further decay to produce lead.